Good morning. Hope everybody's awake. I'm going to talk a little bit about my experience with introducing the Pseudowire technology. It started out 10 years ago now, in 1999, in a coffee shop in Colorado. So this is a brief agenda. We'll go through the history, then I'll show you a little bit of deployments and some future development of technology, basically where we're going from here. So we have to go back in time, and I'm sure that there's a lot of people who were there at that time. I see familiar faces around here. It was like 1998, 99. There was a big rush to deploy bandwidth because people believed that we'd be running out of bandwidth within 1 or 2 years. Didn't quite turn out that way in the end, but we still have grown quite a bit since then. And ATM was what we were deploying at that time, and if you remember, it was expensive, and maximum speed was OC 12s, and OC 48s was on the horizon, but it was going to be really expensive, and so we just needed to find some alternative that was cheaper and maybe packet-based, not cell-based, since it already was very clear, at least in most people's minds, that IP was going to take over the world, and there wouldn't be any ATM left after a while. So we were building a network from the ground up, right? All packet-based services. MPLS was an emerging technology. We didn't have L3 VPN. It wasn't really popular, but at the time, MPLS was believed to be better for forwarding because it would make forwarding simpler. Now it turns out that because IP is really what you want to forward, we actually build devices that forward IP just fine and don't have trouble, much trouble forwarding IP. Although we have, some kind of routing table size issue these days, but we're working on that as well. So in 98 and 99, we believed that MPLS was actually a great idea to move forward in the future. We wanted to actually, create new telecom market competition and new services which would be cheaper to deploy and make them widely available. So, as I said before, the classical frame-relay ATM design was expensive. People built separate networks. Every time you had to deploy a new service, you had to deploy a new network. That was not cost-effective, didn't quite scale as far as support as well. So we want a multi-service backbone, and the other part is that this was, I worked for a service provider at the time, so we really wanted to use existing hardware. It was much easier, proposition to try and create something that would try to use existing hardware than start over and deploy a whole new network and then deploy the service. And we wanted a multiple vendor implementation so that we'd have competition and the protocol would get more popular. Anything that's historically anything that's been kept close to proprietary or fairly closed has really not gone very far. And it's been replaced eventually by something that's easier and more open standard. So how do we design the so-called draft martini, which is what ended up being a very popular name, actually. It had to be a simple protocol. I mean, I had to people would have to read it and say, well, this is not that difficult. Let me just write it up in a weekend or something and do it. It had to use existing hardware when possible. And we'll see. You see this in a little bit in the encapsulation. If you ever ask yourself, why did people create Pseudowires with certain types of encapsulation and how the decisions were made to actually pick the encapsulation? Well, one of the criteria was to say, well, what you have to do when you forward an IP packet. You basically receive an IP packet, you do a lookup, you rewrite the header, and then you put it out another port. And so this had to do the similar thing. So you had to basically receive the packet, rewrite the header, and put out another port, like inserting data, for example, was a function that isn't used in IP. You don't really grow the packet in a router. And so that was something that we couldn't use. So we had to try and avoid functions like that because this hardware wouldn't support it. Now, today is no longer a problem. You can do whatever you want in a packet processor. But at the time, it was a lot more limited. So we wanted to leverage MPLS because we saw that as kind of the future, a very simple system. And we could build a multi-core network with QoS and all sorts of circuit-based, designs or best effort designs, hop-by-hop forwarding. All of that was available in MPLS, and you can just choose whatever model you want, and that suits best your requirements. So the other thing is we want to support existing service provider protocol like ATM, frame relay, Ethernet. At the time, I had marketing people bugging me to create a new cool protocol that run to the CPE, something like MPLS or something like that. And I resisted for many years because I just didn't see the advantage over trying to do something new just to be different. Since there was no real technical or financial advantage to doing that. Okay. There's Windows. Okay, and the other part that you probably are fairly close to customers, so to your service provider customers, so you understand better than a lot more other people, is really the operational model is very important. Trying to go and sell a new operational model, that's not based on circuit at the time, okay. And the new protocol and a new service and all that is much harder than to go to somewhere and say, okay, you can just buy the same thing as your T1 circuits, except now they're cheaper and more flexible and faster. Now, of course, now we have L3 VPN, which I never really thought it would be that popular, but it is technically better than just a circuit, of course, but it was much more difficult to sell and explain. So what was the result? Well, we had a lot of vendors interoperate very quickly because it was simple and easy to implement and accommodate many hardware quirks at the time. Then, I stopped counting in 2001. There was no point after that. We chose, I chose the LDP-based design because I really like the way LDP was built with TLVs. Extensible design. You can just set a bit. If you have to send a new message that an old device might not understand, you set a bit and it's supposed to ignore it, which is rather nice. If you do an upgrade, you don't end up with something closing the link or shutting down the session just because they don't understand something. So you can design new things to basically be graceful to older implementation and in deployment, so you don't end up with issues. We wanted, okay, so initially I started only with point-to-point links because it really was similar to what ATM frame relay. It was easy to sell. It's what people were requesting, and even today there's a lot of that being requested to transport VoIP, internet, and so forth. We wanted MPLS because we wanted to do multi-services. We still had to support ATM and frame relay on this network, and as well support Ethernet. The new transport that was getting very popular was Ethernet. Actually, at the time, I really thought that the most popular would be ATM and frame relay. I never thought Ethernet would be, but I turned out to be wrong. So the other part is the service management, the granularity, scalability compromise. Really, this is an interesting feature of MPLS. Sometimes people don't think about it. You can make it as granular as putting one RSVP LSP per customer link or per customer connection, or you can make one for all the whole PE. So you really have the flexibility to do whatever you want as far as managing your traffic, where it goes, and so forth. It's not built into the protocol. It's a policy the service provider can have. And I've seen all sorts of things, from one RSPT tunnel per Pseudowire to you know, no RSPT at all, and just have LDP-based LSPs and so forth. So this is an interesting experience. When I first started this, I talked to Jakob Rector at the time, and he said, you know, you can put this in the ATF, but I cannot tell you what will happen at the other end of the process. It might, you know, completely change. It might, nothing might be changed, and so forth. So I wanted to show you a little bit what the experience, what happened in the ATF. And, you know, I put in green here a little bit my estimate of what actually was popular, what deployed or not. You know, the first thing that happened is I must have rewritten the document at least like 10 or 12 times. Many times it was rewritten. Of course, first thing that happened, they changed the terminology. We had the initial meetings, and they didn't like virtual circuits, and so they wanted to call this something else, and they called it Pseudowires, and the VCID became a PWID, and so forth. So it wasn't too bad. I didn't mind, you know, I didn't quite care about what it was called. We did actually manage to remain 100% backward compatible. If you go to the RFC, that's the Draft Martini, which is a historical RFC, was published after the RFC 4447, so I don't remember the number, but you'll see that it's really backward 100%. You can still have an implementation implemented this, and it'll work today. It won't have all the features, of course, but it'll still work. What ITF did is add FAC 129 to you know, get a few over different provisioning models, and you know, things like Pseudowire status, which was kind of missing in the initial design, I agree, and that's pretty much deployed everywhere. So we send the status of what the endpoints are along the Pseudowire. They added fragmentation. You know, IP fragmentation is very difficult to be done in a router, so you can imagine that Pseudowire fragmentation is even harder. Fragmentation reassembly, and so there's really very difficult to do in hardware, and therefore, you know, this isn't really been deployed anywhere. The wildcard Pseudowire was to integrate PNNI, ATM PNNI with Pseudowire signaling, and that didn't get popular because PNNI got very little deployment, and so it kind of died before this had a chance. And then we did many special optimizations for ATM. This was really due to a lot of vendor arguments and so forth at the time, and so the ATF solution was to standardize all of them, which I would try to avoid if I were to do this again. If nothing else, is because there's very little deployment of the strange ATM modes right now, but there is some, and it's mostly because nobody told those particular vendors that, you know, this is not the mode that is popular. It just got a little bit confusing. So, but it's not too bad. And then, of course, the FCS retention. There are some folks out there that don't build a router with ECC memory, and so they corrupt packets when they we get forwarded through the routers. So you should always ask your vendor if he has ECC memory. And so somebody wanted to add a frame check sequence in the packet, so that if a Pseudowire packet crossed the router with corrupt packets, you would detect it. This is not really necessary. In most of the major deployment out there have methods to detect any kind of internal correction and so forth. A few other things, minor things, but basically the design was extended from what we started with, added a lot more modes, and it kind of progressed that way. Now, this is some interesting part, experience. Oops, if I had known what, I would have never done this. You know, kind of my biggest headache is this MTU interface parameter. What does it do? It basically makes sure that both handles of Pseudowire have the same MTU, so that you don't end up with a terrible operational headache, like an MTU mismatch, where one side of the you know, of the Pseudowire has a smaller MTU than the other side, and you know, you could end up in situations where you load a web page and everything loads except the images, and now your customer goes crazy because he hasn't figured out how his images are not loading. and gets to your first level support, and people have a hard time figuring out things. And so for that I put this interface parameters. Now it turns out that people don't if it's not broken right now, they don't care too much. They want to just disable it, and there's a lot of very crappy code where people have patched MTUs, and what the interface does isn't really what it's capable of, and so you have interface that report MTU of 1,500 bytes, but they really do 3,000, and so forth. So that kind of turned out to be a big headache. And so, 10 years later, I still have a long call per quarter on this topic. I'm just, trying to even just internal Cisco call to try and say, no, you should not break this. And unfortunately, it just happens that both in the Cisco and Juniper, there is a option to disable this, so you can actually break your network if you want to. So that was not something that sounded like a good idea. It didn't work out that way. And then the last one is a little embarrassing, actually. There was a frame-relay encapsulation header bits. Well, initially, there was a editing mistake in a picture where the second and backend bits were reversed in the original document. And nobody figured this out until like 3 years later when everybody had deployed this already. And then, of course, it was a big argument, but we said, well, it was deployed. Yes, we have to do this transposal function, which is not as efficient as we should do, but we never really changed that. So that was kind of an embarrassing oversight there. But, frame relay is not exactly popular right now, so this is not a big deal anymore. So a couple of deployment examples. So this is one of the biggest emerging deployments. Just one flavor of it right now. This is actually a real deployment in Europe. And what we do here is we have a Metro Ethernet network that's used to replace the radio area network to aggregate node Bs, which are cell sites. And we use a cell site router. In this case, is a small appliance box that will either take ATM and put it ATM over a Pseudowire, or do a circuit emulation over the Pseudowires. This is a type of Pseudowires. We have a Metro Ethernet network, and it goes to a head-end router, 7600 here, that will then put it back out as TDM E1s or ATM over STM1s. And this is used because there is a huge, basically a huge growth in the mobile wireless. And unfortunately, the 3G specification is done over ATM. And it's still the main deployment of technology right now. We don't have 4Gs much at all yet. And so we're growing ATM networks in 2009, and that's like extremely expensive. And so what happened is people are really looking to take those packets, which are over ATM, reassemble them into packets and send them over an Ethernet network instead of ATM. And so this I could never have forecasted, but it turns out that the biggest deployment outside of Ethernet set of wires is ATM now because of this particular application here. The next case is just VPLS for carrier Ethernet networks. This is a service provider that is using VPLS with QoS, and what's happening is actually, let me see here. Yes, this is the right slide. I haven't reversed. What they're doing is running RSVPTs tunnels between every single PE, and they're putting a set of wires into those TE tunnels, the main tunnel and the backup tunnel, and they are connecting I believe in this case is Ethernet. And so they're just basically offering point-to-point service and VPLS as well. This picture shows the VPLS, but they do both. From about 50 different sites. And so let me go back to this one. Okay, this one is a little bit different, but it's very popular as well. This is what we call the segmentation of a big flat network. What you do is you take the flat network, you put MPLS on it, and then you start pulling things out of it. So the first thing, you can pull out L3 VPN and you route the network, but you also have people that used to bridge over this, and so you have to do point-to-point layer 2 tunnels so you can create router adjacencies and so forth. And so what you do is you make this thing called, sometimes people call it hollow core, where you just run Pseudowires over your core and you have complete separation between your customer data and your core. So your customer routing runs on top of your core, either by L3 VPN or by being inside a VPLS or inside a Pseudowire. So this is another very popular deployment. It's both in service providers and in enterprises. I've seen this, universities, many places. Okay, so next I want to kind of go over a little bit the new development. One of the things that we didn't forecast initially, and we kind of didn't think that we would go inter-provider or between different regions or areas with this. And so what we came up with as a solution is called the multi-segment Pseudowire, where it's a similar, exactly backward compatible and the same as the initial Pseudowire. So the TPE1 could be an old PE that doesn't really know anything about this technology and still works just fine. And it will, what we do is we terminate the control plane at SPE1 in this example, and then we start a new control plane and so forth along the way. This has the ability to have a policy enforcement point at a certain point. Has one drawback that you have to go configure every single hop. So you have to configure the 4 PEs in this particular picture, which is kind of undesirable in certain cases, depending on what your policy is. So in order to fix that, what we did is kind of followed a little bit the ATM SPVC model and said, okay, we're going to assign a unique, global unique address at each end of the Pseudowire, so each attachment circuit, which is the end of the Pseudowire. And then what we'll do is we'll take those prefixes, same as like IPv6, except this is 96 bits, and then just advertise them out in some routing protocol, and there's a choice, BGP, OSPF, SIS, so forth. And then what we'll do is we'll just route the signaling message. We just take a signaling message, send it to the next hop, then do a lookup on the address, and then keep sending the signaling message. Now we still have a circuit, so the only thing that's routed like IP is a signaling message. Once that's end-to-end, the reply comes back along the same path, we end up with the circuit again. Now, if the routing changes, unlike IP, we don't have to change right away. We can just sit there forever, or we can, by policy, say, yeah, I'll wait 30 seconds and then re-optimize and things like that. So similar to what RSVP does, I guess, but it's a hop-by-hop routing of the signaling message with a globally unique address, which I've learned from L3 VPN. It actually says that you must have the AS number in the top bits, like the RD and RT in L3 VPN, which didn't quite say that, and so everybody kind of went a different way. So now we end up with RT translation tables. So a couple of things you can do with this is basically you can now, because you have dynamically choosing the peering point, you can actually, if you have a break in one of the Pseudowires, you can re-signal through a different path. Lots of different things you can do. This might not be as fast, but there are other tricks that are faster. So we kind of open the problem to all sort of different solutions that we can do depending on what the requirements are. Oh, last example, fairly quickly. So hopefully this can be. It's a little bit difficult to read, but I wanted to say I've put a lot of OEM support into this system. We can. This is a VCCV trace example. VCCV stands for Virtual Circuit Connection Verification, where we can, since we have a single circuit, what we do is we go and at every hop verify that what the control plane says is exactly what the data plane does. So we we built this and many other Pseudowire status messages and so forth. So it's really very easy for operationally to understand where the problem is. If there is a failure, you'll get notified at the NP exactly where the failure is and what is happening, and then you can use tool like this trace to verify that the path is correct and so forth. And the last topic I wanted to just mention quickly is it's been getting quite a lot of press today is MPLS-TP. So how does it relate to Pseudowires? Well, MPLS-TP is basically everything static. Take MPLS and put it all static. When MPLS was initially designed, people thought, well, the days of static routes in the 1980s is over, and we actually have nice routing protocol, and so we don't need to put static everything back into any new protocol we create. And so they didn't. Of course, you could provision static LSPs, but it wasn't really something that was used outside the lab. So what MPLS-TP is basically going back and putting back all that's needed to run a network that's completely NMS provisioned, centralized provisioning. Everything is static with some OEM that actually fits a static, design. Because if you have no IP, you don't have ping, you don't have traceroute. So now you need something different, right? So Pseudowires are the current, what they call the client in ITU terms of MPLS-TP. There'll be probably other things that we can do in the future, but right now the only thing that people are talking about is running a Pseudowire over MPLS-TP. There's really no change to Pseudowires. They do run over statically configured LSPs, and of course, thanks to some people in level 3 that really bugged me to keep static configuration option in the original Draft Martini, we can statically configure Pseudowires as well. And this is really meant to do lower cost Ethernet access and SONET replacement to replace the SONET models. How does it work in one slide? So MPLS-TP is basically able configuration every router hop. So it's not just the input router, it's every hop along the network you have to go configure. So basically, if you were to run everything in a static IP routing, that's about the same. Redundancy today is pre-configured by basically pre-configuring a backup path, main path, backup path, using an in-band message we will call an AIS RDI for now, that will tell you that one of the links has failed because it's been detected by link light failure on the port or something like that. We can also do the BFD monitoring, which is a bidirectional forward detection, failure detection monitoring, which is just we send a packet and loop it back and see when it fails. We can trigger a switchover. The LFU, it's a label for you, I guess. It's we decided to pick label 13. It's a reserved label that tells when a packet is on that particular LSP, it says it is for you for the next hop. You should not get forward anywhere. And so this is how we do the OEM. If we want to do segment OEM to match the model that we have in SONET. And otherwise, it's just a normal MPLS LSP. So in theory, you could put anything through it. Thank you. If any questions? No questions?
Everyone's still asleep this morning.
All right. Put you out to sleep.
All right. Thank you.